Hi, I'm Norman Wildberger. Today we're going to look at a very practical and important technology for understanding movements, rotations, reflections, and so on in the plane, in the ordinary Euclidean blue geometry. We're going to be looking at reflections and rotations that we've already spent quite a bit of time on. These are grounded isometries, that is, they keep the origin fixed. And today we're going to focus on the grounded isometries and try to understand them completely. So we want to understand what happens with the rotations and reflections together. So we've already determined two important formulas, the compositions of two reflections and two rotations. And here are the formulas. Sigma AB followed by sigma CD is rho AC plus BD AD minus BC. While rho AB followed by rho CD is rho AC minus BD AD plus BC. So two reflections, one after the other, gives a rotation, and two rotations, one after the other, gives a rotation. And this also motivates our definition of multiplication of points. So if we have points on the unit circle, and throughout A and B here are all points on the unit circle, then if we have two such points, A, B, and C, D, then this is how we multiply those points, and it's really just complex number multiplication, or you can think about it that way. And that's appearing here in this formula, and a variant of it is appearing here just with the minus sign replaced with a plus sign and vice versa there. So today we want to extend these two formulas to the other two formulas that tell us what happens when we combine reflections and rotations. And we have to be a little bit careful because then ordering is starting to matter more. This is, however, a very useful thing for people working in design or graphics, anything to do with planar imagery. And the technology that I'm showing you is quite a bit different from the usual one because we are avoiding altogether angles. That's the critical difference. So we're able to get at our transformations exactly without any imprecisions or approximations. And that's a very powerful tool. So if you are working in this domain a lot, think about moving over to this rational point of view. It will empower you dramatically. Now, along with very pleasant formulas for transformations involving matrices and so on, we also like to have some almost physical or geometrical interpretation of what's going on. And a good place to start is with understanding the geometrical way of thinking about multiplication of points on a circle. That's contained in this theorem, that if I represents the point 1, 0, and A and B are any 2 points on the unit circle, and if C is their product, AB, then AB, this line here, is parallel to IC. So any 2 points, A and B, on the unit circle, and we're interested in their product. That's their product down here, C. And the theorem is telling us that we can get at this C by taking a line through I, which is parallel to AB. So we join AB with a line and make another line parallel. And where that line meets the circle in the second point, that will be the product AB. It gives us a very simple and elegant geometrical way of describing the product on the circle. And how can we prove this? Well, let's let A be the point AB and B be the point CD. Then the vector AB there is, well, the difference, C minus A, comma, D minus B. While the vector IC is going to be, well, the difference between the point C and the point I, which is 1, 0. So it's AC minus BD minus 1, comma, AD plus BC. So it's almost the same as just the product, except that we have to subtract a 1, 0. And our aim is to show that these two are parallel. Well, they're two vectors. How do we tell whether the two vectors are parallel? We compute AD minus BC. We compute the product of this times this minus the product of this times this. And if those two vectors are parallel, that's going to be 0. So C minus A times AD plus BC over there minus D minus B times AC minus BD minus 1. And now when we expand this out, simplify a little bit, we get d minus b plus b times c squared plus d squared minus d times a squared plus b squared. So it's still a little bit complicated. And at first glance you might say, well, how is this going to simplify? We want this to be 0. Well, the key is to remember that there's a condition on these 2 points a and b. They're not just arbitrary points. If they were arbitrary points, this theorem is not going to hold true. They are points on the unit circle. That means that a squared plus b squared equals 1 and c squared plus d squared equals 1. This term is 1, this term is 1, and then the total obviously collapses to just 0. So our conclusion is that yes, indeed, AB is parallel to IC. Now, it's a little bit of a surprising and very elegant fact that, in fact, that phenomena that we talked about actually holds or extends to general conics from the circle. And this was a beautiful observation made by Franz Lemmermeyer, a German mathematician, who showed that you could take any conic and you could define a multiplication of points on that conic, exactly in the same way that we've just described. By starting with a point I on the conic, and you fix that point, that's going to be the identity. And then you define for any 2 points A and B on the conic, you define the point C, the product, by the rule that IC should be parallel to AB. So it's a very practical thing. You just take this line AB that you've constructed between A and B, you draw parallel to it through the fixed point I. Whoops. And then the other place where that parallel meets the conic is the product AB of the 2 points A and B. And beautifully, this defines a group structure. So associativity, not entirely obvious, it's some kind of consequence of Pascal's theorem, is a very pleasant aspect of it. And it's moreover a commutative group structure. That's kind of obvious because it doesn't matter whether you're taking A or B first. The construction shows that it's going to be AB equals BA. So this is a general phenomena for a general conic, including hyperbolas, parabolas, ellipses. Now we need just a bit more notation before we get to the general formulas. So if A is a point on the unit circle, and it's of the form AB as usual, let's define the conjugate to be A bar. And that's by definition A minus B. So we negate the second coordinate. And that's, of course, familiar to those of you who have studied complex numbers. And if A is actually on the circle, well, this turns out to be the same as A inverse. That means if you multiply A times A inverse, you will get the identity point. And let's introduce a little bit of a shortcut notation. So instead of writing sigma AB for the reflection, let's just write sigma A. Instead of writing rho AB, let's just write rho A. So that our reflections and our rotations can be indexed by simply points on the unit circle. Well then, the two formulas that we already have can be stated this way. That sigma A times sigma B is rho A bar B. And rho A, rho B is rho AB. So this was the situation where you have AC minus BD, comma AD plus BC. And over here, the slight variant where the plus signs and minus signs interchange places. So it's a AC plus BD, comma AD minus BC. And you can check that that's what you get when you take that point A bar times B being CD as usual. Okay, so now we want to move on to what happens when we multiply reflections and rotations. Okay, so the order is going to matter. Let's start with a reflection followed by a rotation. So sigma AB followed by rho CD. There's the matrix for the reflection, AB, B minus A. And here's the rotation matrix, CD minus DC. Okay, you do the product, you get this matrix here, and you see that that's a reflection matrix indexed by AC minus BD and AD plus BC. It's a reflection matrix because these two are the same and these two are negatives. On the other hand, if we do it the other way around, we do a rotation matrix first, rho AB, followed by sigma CD, the reflection. Well, you could do the matrix multiplication again, and you'll see that you get sigma AC plus BD, AD minus BC. So the same two quantities are appearing. There's the product of A and B, and there's the product of A bar with B. But this time they're reflections. The other two cases, we ended up getting rotations. Here we're getting reflections. So when you mix rotations and reflections and multiply them together, you get reflections. It's a little bit like even and odd when you add. Okay, so when you add two evens or you add two odds, you get even. That's like the rotations. And if you add even and odd, then you get odd. That's like the reflections. So the reflections are sort of like odd, and the rotations are a little bit sort of like even. Okay, so now we can describe the group of blue grounded isometries. Blue referring to Euclidean, and grounded referring to the fact that the isometries are fixing the origin. Okay, in our notation, A is a point AB, which also might have a half slope h. It's on the circle x squared plus y squared equals 1. And so associated to it is a reflection sigma A and also a rotation rho A. So here are the four formulas. Sigma A followed by sigma B is rho A bar B. Rho A followed by rho B is rho AB. Sigma A followed by rho B is sigma AB, while rho A followed by sigma B is sigma A bar B. So if the first thing's an A and the second one's a B, we're always getting products A, B's, but sometimes with bars and sometimes without. We get two rhos and two sigmas, and we get two ordinary multiplications and two sort of twisted multiplications with a conjugate as well. So this is expressed using the multiplication of points on the circle. And I remind you, this is the formula there. So AB times CD is AC minus BD, AD plus BC. And the other ingredient is the conjugation. The conjugate of AB is A minus B. So this contains sort of all the information that summarizes the group structure of the grounded isometries. Every grounded isometry is either a reflection or a rotation, and here's how they all multiply. Okay, so those formulas are useful for us because we can work algebraically, but we can also work geometrically. In other words, we can use constructions, relatively simple constructions, to process what composites of rotations and reflections are going to be. And I want to show you how that works. But in order to make it sort of more smooth, we're going to introduce a little bit of notation to specify these grounded isometries in terms of points on the unit circle. So if we have a point A on the circle, if we draw a little square around it, let's use that to represent the reflection sigma A. And if we have a point and we draw a little circle around it, let's use that to denote the rotation rho sub B if the point is B. So that means that we could describe rotations and reflections by little diagrams like this thing here. So here we see 3 points, A, B, and C on our unit circle, and this represents the rotation rho sub A. Let me remind you what that does. So if here is our sort of circle, and we're orienting, so it's pointing towards the identity, if we apply rho sub A to this, what's going to happen is that that point there at the identity moves up to A. So the circle is just going to rotate like that. That's what the rotation rho sub A does. This thing here represents the reflection sigma sub B. What does that do to a circle? Well, it's a reflection. So it reflects, but it also sends our identity, 1, 0, to the point B. So in all cases, the point on the circle is where the identity ends up after you've done the rotation. So, or the reflection. So what kind of reflection is it going to be? We have to reflect in such a way that this point here gets sent to this point here. Well, if we have a little ruler, so we'll connect those 2 points, then what we're going to be doing is wanting to reflect in a line that's through the origin that's perpendicular to that. So maybe in this case, something like that. So that would be an axis of reflection. The axis of the reflection, sigma sub b. That would send this point to that point. And what would it actually do to the points, say on the circle, or actually the entire plane, but we'll just represent it with this little sort of model of the part of the circle. All right, so what happens to this thing? Well, I have to reflect it in a line that was sort of perpendicular, something like this. Okay, so I'm going to take this thing here and I'm going to reflect it in this thing here. So maybe I can just sort of do it like this. If we go back there, okay, then you see that the part of the circle that was originally aiming towards here is sent to pretty well B, maybe adjust it like that. And otherwise, you know, it has been a reflection, so things have been transformed across the mirror image. And over here is rho C. That's easier to describe. It's just a rotation that starts with the plane like this and ends up going like this. Starts there and ends there. All right, so now we can try some computations using a diagram like this. So let's try to describe this composite isometry. Rho sub A followed by sigma sub B followed by rho sub C. Let's do it algebraically and sort of geometrically at the same time. So rho sub A, sigma sub B, let's do those ones first and then followed by rho sub C. So we're going to use our formula for rho followed by a sigma. Okay, so I remind you that that was a sigma. And it was a sigma with what underneath? Well, it's going to be A bar times B. So A bar times B. And then we still have to multiply by rho sub C. So let's see if we can sort of do that first step and compute sigma A bar B. So we need to find the point A bar B on our diagram. Okay, so let's do that. So here is A, and finding A bar is just finding the conjugate of it. So that'll be down there. So there will be A bar. And now we have to find A bar B, the product of A bar with B. So we should draw a line through those. A dotted line like that. There's a line. And then what do? We look at the line through the identity, which is this one here. That's the identity, which is parallel to that line. So we're going to move that up in a parallel fashion, about like that. Draw a line. Okay, and that point there will then be A bar B. A bar B. And so what we have over here, sigma A bar B, is we have a reflection at that point. So we want to maybe describe the reflection. We could put a little square around it. It's a reflection, so we'll put a square around it. Okay, so now let's go to the next step. The next step, we want to calculate the product of this reflection with this rotation. So it's the same kind of formula. We're going to get another reflection, but now it's reflection followed by rotation, so we don't have any bar. We are just looking at A bar B, that times C. Okay, so it's a reflection in this point, but we have to find where this point is on our picture to be able to sort of see what actually happens. Okay, so where is that point going to be? Well, we've just found A bar B, it's right there, and there's C. So we're going to find the product of those two. So let's do that by joining those 2 points. Joining those 2 points with a little line. Okay, and then we're going to draw another line that's through the identity parallel to this. So we'll have to move parallel, perhaps like this. Okay, there's the line. And it looks like there's the point A bar B C. We don't actually need brackets because multiplication is associative. And the final result is a reflection there. So there, that's the final result. Let me circle it. The effect of doing row A and then sigma B and then row C is to find this object here, which is the reflection determined by that point. So let's see if this actually works geometrically. Okay, so we're going to start here. And let's actually perform these three, okay? So in order. So first, row A, that's rotation by A. That means the point I will go to that point there. So we just have to point our arrow towards A. Great. And now we're going to perform this sigma B reflection, the same kind of thing that we did before. So I remind you the axis was something like there. So I have to take this thing here and I'm going to reflect in this axis. Let me put it there. Okay, I'm going to reflect in that axis. Okay, something like this I get. Okay, that was the reflection sigma B. And now I have to follow it by a rho sub C. What is that going to do? So that's the rotation that would take the identity down to there. So that much rotation. Well, that much, about the same as that much. I could actually transfer that over there if I wanted to, but I'm just going to eyeball it. I'm going to get that. On the other hand, what is this thing? Well, maybe I should rewrite it as sigma A bar B, see, because we don't need the brackets. That's this thing here that we've got. Well, we see that that's pretty well what we've got here, because if we just did this reflection, it would be the reflection that starts with the plane like this, and then reflects in what? Reflects in the bisector of this line joining these two things. That would be a line like this. Okay, that's the actual axis of reflection. The axis is not through that point. That's where the image of the identity goes. The axis is the bisector of the segment joining them. Okay, so there's the axis, roughly about that. So it's something like this. So if I take that, like this, and reflect in it, okay, then I get something like that, which is what we got before. So you can have a lot of fun now. You can see that, yes, you can calculate with the formulas that we have because we know exactly how to write out the products and the conjugates using the essentially complex number multiplication. But you can also do things geometrically. And that has the advantage that, well, you can do quite a lot of points and the algebra doesn't get too complicated. But either way, it's very pleasant to practice working with these grounded isometries. But our story is not yet completed. There are still two more things that we would like to do. One is to describe this story not just in terms of the points A and B, but in terms of their half slopes. Remember that every point also has a half slope. So it's natural to ask, well, what do these group operations look like at the level of half slopes if we just know half slopes of things instead of the actual points on the unit circle? So that's one interesting question. And the other is, what happens when we go to the big group of isometries? So we start with the plane in a certain configuration, and then maybe we perform rotations, but we also perform translations. And maybe we reflect in lines which are not just going through there. Maybe we reflect in this line. Get something like this, or like that. Okay, so there's more general isometries, and they're not all grounded, and we need to get some technology for being able to do that, and that's very important for people who are doing graphics and video games and so on. So because we want to move around the entire plane. So that's what we're going to do next time, and I hope you're going to join me for that. I'm Norman Wildberger. Thanks for listening.